presentation up until now? Raise your hand. 1, 2, 3, 4. Okay. No, that's fine. People after their presentation are the chillest people, right? Yeah. But before, okay. This is a special session. I don't know if you guys know. All right, so we're streaming. Well, I was about to say this. This one is a bit historical because we're about to hear motivations for formally verifying a verifier. We prepared this session, so Ben prepared this presentation for us to understand the why and the usefulness of such approach. So I'm very happy to hear what you have to tell us. It will be followed by a presentation that gives an example of formal verification in practice, and then we'll have a session among us to try to discuss this in a more like back and forth way. So please allow me to introduce Ben Livshits.
All right, thanks very much and welcome back. So this is going to be a little different from what you heard this morning in terms of both topics as well as the format. We'll try to improvise a little bit later in the session because we wanted to facilitate an open discussion around where we can take these ideas and how to take them further, whether there are standards we can apply here, whether this is the right time to do that. Maybe it's too soon, maybe not. I guess we'll find out. But before we do any of that, I wanted to give you some genuine motivation as well as share some of the thinking we've been that's been there for some of us at ZK Sync. So just a little bit about myself, if this is working. Maybe not. There it is, okay. So just a couple of words about myself. I run research at ZK Sync, Meta Labs, so one of the makers of zero-knowledge rollup that's out there. I also am a professor at Imperial College London, so I kind of straddle this industry-academia divide and have been doing that for quite a number of years now. So my background is not in cryptography. It actually comes closer to things like programming languages and reliability and verification, as well as system security. But the last 4 or 5 years, we've been working a lot more actively on topics related to blockchain, starting from analyzing DeFi applications to flash loans to a variety of other things in the last several years as well. There it is. OK, so the path of ZK. What is the path of ZK? Simply put, it's really to move away from wasteful execution, wasteful multi-execution, if you will, that happens on the underlying L1, be that Ethereum, Solana, what have you, and move away to something that ultimately should, over time, be more sort of affordable in a certain manner of speaking, and move to this domain of ZK-proof production. And when I say ZK-proof production, I primarily envision, sort of massive scale kind of operations, right? So you basically have some sort of a cluster, something in a cloud, that kind of thing. And this is sort of my main mental picture when it comes to these things. Of course, we're also interested in lighter weight proving, but that's perhaps a conversation for a different time and a different sort of story, if you will. And of course, none of these things should be too surprising. We have sort of significant efficiency problems. We have sort of ongoing, seemingly never-ending competition in terms of new proof systems being proposed, interesting sort of combinations of software efficiency as well as increasingly hardware efficiency considerations. And on top of that, and this is really what people in this room typically would focus on, at least a subset of people in this room. But what I'm here to basically tell you is that that's sort of not the only thing, right? So So on top of that, you also have reliability and correctness problems. And in some ways, I would say that those have been overlooked for a little bit in this domain, in this space. And why are we focusing on this now, right? And so in principle, people have been, developing proof systems and on some level taking them to production, right? And, developing large software packages in languages like Rust. I mean, in some ways that's not new. It's been going on for maybe, at least a couple of years, maybe even 5 years, depending on how you count it. There are several reasons for that. Of course, one of them is the fact that, zero-knowledge rollups are coming into the prime, right? And it's not just us, it's also some of the competitions, such as Scroll, Polygon, AdStack, a few others here and there, Linea, a few others here and there as well. All of those companies are building really complex software, right? And sometimes they're also combining that with interesting hardware-based experimentation, all the way from using specific GPUs to increasingly moving towards things like FPGAs and maybe eventually even ASICs. So that's getting very interesting. That's one point. The other point is that, we are still at the stage of where we have the training wheels on, right? That is to say, we are still in a very centralized deployment situation at the moment, right? Despite what people have been saying for quite a while about, this progression of starting with a centralized sequencer and then decentralizing that over time, we are still largely in a centralized setup. And so as we consider kind of this progression, right, the path of decentralization, if you will, this is how it's likely to unfold, right? This is not quite a promise. I think different projects will do it slightly differently. They'll use different approaches to just about everything. I mean, you can sort of go and see what people are doing for even sequencer decentralization. You'll see a variety of approaches that are likely to be put in industrial practice. So I think, decentralized sequencing is pretty close. It's within shooting distance, right, for a variety of these projects out there. I think where it gets a lot more interesting is what I have here on the right side of the slide, which is to say decentralizing the proving process, right? And, here we have ideas from how to utilize prover pools, how to open them up to external participants, all the way to what's called prover markets. And that, of course, combines the relative openness of these things and perhaps permissionless participation with the idea of incentive design and mechanism design. So we have a number of companies in this space. I see people from Gavelat, for example, but not only, right, trying to basically foster innovation around prover markets, right? And the idea here, in a nutshell, is quite simple. So by opening up participation in prover pools and prover markets, will hopefully lead to, this will hopefully over time lead to competition among proof producers, both on the software side, in terms of also energy efficiency, but also hopefully on the hardware side, right? And so over time, this kind of competition will lead us to a situation where proving in a general sense becomes more affordable. And these savings are there to be passed on to the end user. And again, when I say proving here, I'm primarily motivated by the goal of proving Ethereum blocks, right, or batches or what have you. But essentially, this is the workload I'm talking about. So think about a bunch of operations on Compound or Uniswap or what have you in DeFi, and then that makes it its way into rather batches that are proven on this kind of hardware, custom-made or otherwise. And so this is, a couple of reasons why this is now heating up in a really interesting way. And so here's the key observation, right? So we are not quite there, but we are perhaps on the precipice of moving away from a situation where we have a trusted prover setup effectively, right? I mean, running in, our data center, let's say. That still gets verified on the underlying L1, be that Ethereum or something else, or like Bitcoin, which is what we heard about this morning, to a situation where, it's likely to become a bit of the Wild West, right? So we'll be having proving running on untrusted hardware, and furthermore, we're not necessarily thinking about doing any sort of remote attestation against these provers either. So if they want to go and change the code, the underlying Rust code, they're most welcome to do so as well. And so like what stops the situation from becoming total anarchy? Well, it's the verifier, of course, right? So the beauty of this setup is that, you could have found these proofs in the street for all I care, and then it's up to the verifier to ensure that total anarchy does not result out of this situation. Yeah, I sort of talked about, the left side portion of this slide already, and then what happens if the prover suddenly becomes malicious, Byzantine, what have you, or for that matter, what if there is a mistake somewhere there, right? So let's focus just a tiny bit on the verifier, right? So now I have a little table that we have from a preprint that we just put online on ePrint yesterday morning, so I'll have a link to that as well. But so there is a table that lists information about the verifier for several projects. So ZK Sync Error, Polygon Hermes, Tycho, and Linear, some of the kind of leading rollups out there, as well as information about the lines of code. Well, so is this a lot of code or is it not a lot of code? Sort of depends on how you think about it and how you look at it, right? So in the grand scheme of things, compared to like, giant piles of Rust code that go into the prover, maybe this is not so bad, right? I mean, what is it, 1,700 lines of code? Doesn't sound too terrible, does it? And of course, the question is like, what kind of code is it? And I'll give you some examples in just a second. But, the hope here is that what's going on, right? So in a sense, this is as mission critical in this space as it gets, right? We would love to make sure that the verifier is as robust as it gets. And at the same time, the size of the verifier is not quite overwhelming, right? And so in a certain sense, let me give you like a real world analogy. So let's say you have a car and there's all sorts of bells and whistles in a modern car, all sorts of fancy electronics, and the stereo system is doing crazy things, and Bluetooth is connecting to your phone, all sorts of things are going on. But like, there are certain things that are extremely mission critical. Like you really want your brakes to work under a variety of interesting circumstances, right? If it's rainy outside, the brakes should work, and so on and so forth, right? And this is where people have chosen to use verification techniques to focus on the mission-critical portion of the system, right? So maybe there are other things that are outside of this kind of scope, but there is a significantly reduced portion of the code, relatively small in size, that is super, super important. And my claim here is that the verifier is probably it. So this is code that's written in Solidity. It's actually mostly YUL, right, which is sort of this inline assembly within Solidity. But what I'm claiming here is that this is a nice problem. And this is a smaller problem than most others that are found out there in a certain way. So this is a problem that's both very important and also potentially solvable. So let me go a little bit again. So I'll start, becoming slightly more controversial for at least a few minutes. You often hear ZK is just math. Well, the reality is that it's not just math, right? So this is deliberately kind of unreadable, if you will. So just, a little bit of code from Polygon and Tycho, sort of chosen somewhat at random, right? This is the kind of code you see in the verifier. And so my point is that it's not just math in a couple of different ways. I mean, first, these are complex distributed systems, right? So if you think about the process of proving, you have to worry about, how do you provision enough specialized machines that have GPUs of a particular shape, right? So how do you ensure that the availability is as close to 100% and so on and so forth? And these are the kinds of concerns that come in just about any distributed systems, right? This is kind of, very common in cloud-based deployments of systems, over the last 15 years or so. This is nothing new. But on top of that, you also have software complexity. And some of the software complexity I claim here comes from this kind of code, right? It's sort of a wall of difficult to interpret code, which is, maybe good news and bad news, right? And that it's not so trivial to interpret, but at the same time, it's sort of a finite amount, if you will. On top of that, we did some recent work, and on the right-hand side of the slide, you see a snapshot of our recent preprint that's under submission at the moment, looking to the bugs in zero-knowledge systems. And a few high-level points come out. So we looked at over 100, almost 150 bugs, I think 141 bugs that have come from things like recent audits in deployed or like pre-deployed, zero-knowledge systems, right? Which basically highlights my point. It's not just math. It's really, software development, sort of the way we know it, which is to say, the underlying algorithm could be perfectly fine. It could satisfy our security assumptions, but what actually gets shipped could be pretty far from it. On top of that, of course, there's the added complexity of auditing code in this space as well. That is to say, it's really difficult to audit. We sat down with one of the sort of main auditors in this space yesterday evening for quite a while talking about some of these topics. So, I mean, there are some traditional challenges when it comes to auditing that apply here as well. So, for example, maybe these software systems get audited once every 3 months, once every 6 months, but of course they change maybe weekly, right? And so what is deployed versus what was audited are sort of two different software artifacts, aren't they? But if you're interested in this, and if you're interested in finding some of the specific kind of bugs that we cover in this report, you'll be able to take a snapshot of the slide in just a few minutes. But here's a slightly more controversial point still, which is to say, I mean, people in the, oops, what's going on? Sorry about that. People in the blockchain space really oftentimes like to complain about things like SGX, saying, it's a broken technology, we don't like to trust Intel, it's been found to be buggy so many times, and so on and so forth. Well, in a certain way that's true, but let's try to kind of take a longer time perspective here as well. Let's apply a longer time horizon. So there's this report that we put together in the last several months that's, as I mentioned, is under submission. And here's a bit from a paper, and you can see the paper over here on the left. This is one of the surveys. I think there are 2 out there of bugs in SGX, right, which is probably the most widely deployed T that's out there, that's been out there for quite a while now too. And you see sort of, some papers, some bug reports, and they're classified in a variety of ways. This is what this kind of table is supposed to show you. Basically a variety of attacks, right? And so this is like dozens of attacks over about a decade. And by the way, these are primarily, as far as I know, focusing on things like side channels, which is to say confidentiality, right? Privacy concerns as opposed to integrity concern. So philosophically speaking, and again, I know that this is probably going to displease some of you in the audience, like which one is better? And my point is that it's sort of hard to say, right? In terms of the real artifact that's out there in production, a little bit hard to tell. So if we have perfection when it comes to implementing zero-knowledge algorithms, amazing. I think it's quite easy to make an argument that, well, that's what we should go with. But if both of them are fundamentally buggy, and it's not entirely clear which one is more buggy on a good day, well, who the hell knows? Here's an example, and perhaps the fonts are a bit too small, but let me just maybe try to point out a couple things to you. But essentially, we kind of went out and looked for bugs in existing verifiers that were deployed. This is from, let me see, I think this is Trail of Bits, if I'm not mistaken. This is from a linear audit back in 2023, about 6-7 months ago, give or take. And so you can go and look at the report. We have it in the PDF. This is Open Zeppelin. The link is right here, in fact, right? So this is a bug in one of the sort of key rollups out there that was found through an Open Zeppelin audit, and there are some other links if you want to find some of the recent audits of other systems. There was another one that was highlighted quite a bit back in 2021 that AdStack did. So there's a bug in recursive proof verification. There are some details out there as well. There's a report from March 2021 that talks about this also. I don't remember who the auditor was for this one. Maybe it says there somewhere, but again, it's in the report that we put together as well. So my point is that I'm not talking about just a theoretical possibility. These things happen. When it comes to the verifier, these concerns I'm not trying to sell you on something that's, sort of far-fetched, let's say, right? Given that audits of this kind have found problems in verifiers in the past, going back to specifically 2021. So the question is like, what to do? How do we do better? And so when it comes to ZK properties, right, so these are typically the properties we consider: completeness, soundness, and finally proof of knowledge. And I hope the fonts are not too small, but I'll go about the high-level stuff over here just to kind of make sure we're on the same page. We've, over the last, maybe couple of months, we've thought about, what to do about it, and specifically which verification technologies would apply in this kind of context. And there are some kind of favorites from the last, several years. So, for example, people look at Lean. Lean 4 is getting quite popular. People in this space have looked at some of the tooling from a company in Illinois called Runtime Verification, so this KEVM framework specifically. And last but not least, and this is our sort of weapon of choice, there's a system called EasyCrypt that's been used to verify ZK protocols in the past with some success, and this is kind of our focus here as well. Again, in the report, we go over some of the reasoning behind that, but the reality is that, we kind of need to have the kind of probabilistic logics, probabilistic reasoning that reasoning about proof of knowledge requires. And this is why sort of the typical propositional reasoning on Lean is not quite sufficient for us. If it were sufficient for us, we could probably find more people who could do it, let's say, and also gain perhaps more efficiency through proof reuse, blah, 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 lemma reuse, things of that sort. But so over the last 2 months, we've basically centered around this approach that utilizes EasyCrypt, and I'll give you some examples of that as well. Yeah, and this is essentially what this says, which is to say, to go beyond just functional correctness, where Lean could have been an easy and widely used option. EasyCrypt is a good choice for targeting soundness and proof of knowledge properties of ZK verifiers, right? So this space is tricky. In a certain way, it's slightly misaligned with the kind of mainstream approach that's used out there in the verification community. Yep.
Hi, I was at Hack's high assurance crypto software a couple of months ago, and someone was, so it says there that EasyCrypt has built-in support for imperative modules. Someone there was talking about an approach for using Lean to verify imperative programs that looked very promising, so it might be worth.
It's not so much imperative versus declarative, it's the underlying logic that you use, right? So again, if you're after probabilistic reasoning, EasyCrypt, I mean, it sort of pushes us in this direction slightly away from Lean, right? So okay. I think you're talking about sort of a different dichotomy. If I heard you right, it was slightly difficult to hear, imperative versus declarative. Is that kind of what you were getting at? Or
yes, yes.
That's a different dimension, I would say, almost altogether from this.
Yeah, I mean, EasyCrypt does have a lot of advantages for verifying crypto.
I'll give some examples that hopefully will illustrate this as well. So this is just an outline of our approach that we've taken thus far, and this is sort of our program for the next several months of doing this. So we start with our own verifier, right? So the verifier for ZK Sync era, which is about, 1,500, 1,600, 1,700 lines of Solidity code, which is mostly YUL, which is this inline assembly I mentioned before. So basically we do code extraction. That is to say, we convert automatically through transpiler the existing YUL code into EasyCrypt statements. Right, so this is how we preserve the original semantics. We then use EasyCrypt abstractions to define a mathematical specification of the verification function. And I'll illustrate this through an example where I'm trying to connect code with the math, if you will. So then we use program logic, so I'll give an example of that as well, to effectively prove equivalence between the low and high level implementations of the verifier function. And then by relying on mathematical abstraction, we basically derive the necessary security property for the high-level implementation of the verifier as well. So let me see how I can illustrate this. Right, so this is basically the equivalence between the high-level and low-level verifiers, which allows us to establish the security for the low-level EUL implementation. So this is like extracted, for the purposes of illustration from the much larger verifiers. So this is talking about Lagrange polynomials. And so what we can do is we can define this kind of operation in EasyCrypt that's shown to us at the bottom. As part of this process, we would automatically convert the EUL code that's shown here on the left to the EasyCrypt code that's shown over here on the right. And you can sort of, roughly match these things, right? They're not too far apart in terms of at least syntax, but the semantics are actually quite different. And that, you sort of have to worry about, like, for example, the semantics of addition in finite fields. You have to faithfully represent that in terms of how this is interpreted in EasyCrypt on the right. So there's quite a lot of machinery that doesn't meet the eye if you just focus on the syntax over here, if you will. And then, in terms of reasoning about this, at last, we basically have to prove the following lemma, right? So this is, and this is explained over here at the bottom. So let me just read this. So the result of the computation of this function called evaluate Lagrange poly out of the main is equivalent to the result of computation of Lagrange polynomials. And then there are some kind of details that are at the bottom here as well. And there's quite a number of other details about sort of, value conversion and the semantics of these brackets, both curly brackets and square brackets, and a variety of other things as well. But at a high level, this is essentially combining mathematical reasoning about, again, mathematical objects with reasoning about the code. And again, this is all in miniature, right? We're not trying to scale this up to millions of lines of code. This is not the aim here. The aim is to do relatively sort of closed world kind of reasoning. There are some other bits and pieces. I'll just highlight a couple. So effectively, you have to model the EUL memory state. You have to worry about the data type side effects. You have to potentially worry about modeling gas usage, right? And potentially doing that explicitly as well. So this is not without its own challenges. But again, let me highlight for the nth time that this is not something that we are trying to kind of send out there for, applying to every smart contract you write. This is a relatively dedicated, specialized task. To pop out just a bit, look, people have tried to bring ZK and automatic reasoning, verification, formal methods together for quite a while now, right? Specifically in the last, 2-3 years, we've seen a lot of efforts focusing on reasoning about circuits, looking for under-constrained circuits, over-constrained circuits, right? Circuits are effectively specification of sorts. So debugging the specification is sort of, if you will, this is the way I would characterize those efforts. And, there are companies like, for example, Veridice that are quite active in this space as well. Some of the tooling is getting better and it's more practical. We are also working on some of this, but this is not this effort, right? When it comes to the prover, we've seen, certainly the audits, and I highlighted some of the audits, and there are more of these things in the paper as well as languages that aim to achieve end-to-end correctness, some efforts from a variety of sources, academic and otherwise. The focus of what I'm talking about here and the focus of what's described in this draft as well is verifying the verifier, right? So the Ouroboros of ZK is exactly sort of this picture. This is what I want to call to your mind. Just to give you a little bit more, if you are sort of looking for things to read, so this is the first thing I mentioned. Sorry, this is right? This is what came out on ePrint yesterday. This is the work we did on finding bugs and classifying bugs in ZK system from March this year. And also just to kind of, if you're interested in the broader kind of prover decentralization space, we've also been doing work on mechanism design. And this is the last thing I have highlighted here. A lot of work happening in the last, several years. But let me just finish by saying that verifiers are as mission critical as it gets in this space, right? If you want to have this separation rather between the untrusted prover and a verifier, that's the last line of defense, we really need to focus on verification tasks that verifier gives us. We've seen other instances where the formal methods community and ZK have sort of crossed paths in the past. Now I think is a great time to actually do this again. And this space gives us the kind of problem shape that oftentimes you want. That is to say, it's relatively small, it's relatively self-contained, it's well aligned with sophisticated reasoning. It's also at a time where the progress in I don't know, cloud capacity and all these other things allows you to just focus on much harder verification tasks as well. So the call to arms is exactly that. I mean, I think people who do ZK, both academically as well as in industry, should embrace formal verification. And the other way around too. So people who do formal verification should go and find interesting problems to work on in ZK. Thank you.
Okay, do you have questions? Questions to Ben?
Hi, I'm Eli Baum from Boston University. So you mentioned like an auto-compilation process from the code into EasyCrypt, and I'm curious how you figured out or determined what statements to prove. Is that part of the auto-compilation from like asserts, or did you have to manually encode the theorems?
It's a good question. So, I mean, there's quite a lot we're meeting here as well, right? So, I mean, transpilation into EasyCrypt is a relatively simple sort of syntactic process, right? Like one AST becomes another AST, you just dump it and it's there. I think a deeper question here is how do you structure your lemmas? How do you structure the proof process? And there is a bit of sort of manual work that goes into that we are still on some level mapping out. It's a process, right? I don't know. Do you want to, Denise, do you want to just add a couple of words about that?
So essentially, the whole process is guided by the proof of equivalence. So you have the high-level description of the function and then the low-level description. And like once you have set these levels up, then this is what guides all the intermediate lemmas. But technically speaking, the moment once you have algorithm transpiled to EasyCrypt, then there is already a functional semantics. Now you just need to prove the refinement. I hope this answers the question. I don't know who I'm speaking to.
Yeah, so what's your opinion on the fact that verifiers for different proof systems have very different levels of complexity? So Grot16, for example, is relatively easy to verify compared to the Plonk-based systems because yeah, because the latter involve a lot of polynomial evaluation to check custom gates and so on.
Yep. So this is an excellent topic for later discussion. So I think the plan is to have another talk after this one, and then we'll kind of open the floor for broader conversation. So we have our own path that we're trying to follow, just because there's an artifact that we deeply care about, right? But then the question is, like, as a community, what else should we do? Should we focus on Groth? Should we focus on bulletproofs? Is there a number of artifacts we can sort of, focus on, and both development methodology as well as actually, like, I don't know, pieces of facility code that people can reuse. Like, what is the right path? And I think, we should just, we'll open the floor for some of these conversations in about half an hour, I think.
By the way, as someone who's been most vocally critical of T's, I completely endorse your argument. We need to verify the verifiers. So T's are definitely bad. ZK may be bad in practice as well.
I mean, I think T's provide a nice counterpoint, to sort of this argument, right? Which is to say it's not just math, and secondly, implementation bugs ultimately plague you for years, right? And which has been the case for T, of course, most visibly. But again, we're quite early on this ZK journey, right? Like, we don't know where the space will be, 10, 15 years from now, right? And if there is another kind of, if there's like a Pentium bug of ZK, you want to get ahead of that problem, is what I'm trying to say. There was a hand. Yeah, please.
Sorry.
Rowhammer probably would have been a better example, not the Pentium bug, but you get my point. Yep.
I think the sort of end-to-end verification of actual code is really interesting. I'm just a casual follower of formal verification. Can you repeat again why EasyCrypt is more amenable to your problems than Lean?
Do you want to speak to that?
So we care about a probabilistic setting, and when it comes to verifying serious probabilistic protocols in a purest cryptographic computation model, then EasyCrypt is the choice. It's the tool which illustrated like the most convincing examples of verifying like large-scale protocols and like on different levels of abstractions. From the Kyber would be one example.
I suggest that that conversation we continue it in the session in half an hour, because So we're going to continue this conversation in half an hour because we want to hear from Marcin, and also because it would be great if we can get into like concrete examples and making in our minds, like as engineers, what would we be doing? Very interesting to know about it. So we'll dive deeper. Thanks again.
Thanks very much.
All right, so we switched a little bit the order. So